Thanks, Phil. Good evening. Thank you guys for taking your precious evening time to join me. I'm happy to be here to talk to you about Arctic issues. But before I begin, I actually have a little confession to make. I can't operate the slides. So here's my confession, and this is what I use to kind of frame my story tonight. So not only am I a Southerner who several times travels to the North for a variety of work purposes, but I'm also an American. So, I started working in the Canadian North as a young adult, as an undergrad researcher, and I've never looked back. So, fast forward several decades later, I'm now a scientist, and I'm a mom of 3 young children. So here's my paradox, the first of several. How can a very family-oriented person, someone who cherishes their young children, leave their family several times a year to travel, at great distances to the North? That's my first paradox, is my own paradox. And this is the easiest one to answer of tonight. I do this in my personal life because the North really calls to me. It's really become a fundamental component of my fiber, and I think it's really fundamental to the social fibers of many Canadians. We look to the North as a source of purity, of wilderness, of adventure. But I also do this in my personal life because I believe really strongly in the research questions that we're asking. And what I want to talk about today is how an issue of change in Canadian land that affects really fine scale, small scale organisms and land and water movement can feed back and scale up to affect the entire globe. So what I'm going to do today is define Canada as a permafrost nation. And I do this because permafrost covers most of Canada. So more than half of the Canadian land base in some form or another is underlain by permafrost. Permafrost is just perennially frozen stuff in the ground. It can be soil, it can be sediment, it can be rock. And it stays frozen year-round, and we call this permafrost. So in the North, in the far Arctic, it's continuous. It underlays all of the land. And then as we move further south in Canada, this permafrost becomes patchy, it becomes discontinuous. So in one form or another, all of these different zones of permafrost region total up to more than 50% of our country. We truly are a permafrost nation simply by area, by distribution. But even in the far north, where permafrost is continuous, it's pretty patchy stuff. So this is just a cartoon diagram sort of looking into the earth, into a soil column. You can see it's made up of a variety of different kinds of earth materials. We've got frozen rock intermixed perhaps with these massive ice wedges. All of it's frozen, but it's very heterogeneous. The other really important thing to remember about permafrost is it's underground, it's subsurface. So permafrost is not something you can see from walking around the tundra or a boreal forest. It's underneath an active layer or a seasonally thawed layer of soil or peat or sediment. And because it's subsurface, it's actually pretty hard to measure permafrost. We can't see it. We have to go digging for it. Luckily, several decades ago, that's exactly what a network of permafrost scientists did. They dug all over the far north of Canada and Russia, and they started measuring permafrost temperatures at depth. What I'm showing you here are some of the most famous borehole temperature records in Alaska, ranging from sort of discontinuous, sort of warm, quote-unquote, permafrost temperatures all the way up to the far Arctic, the far north slope of Alaska. And across all of these boreholes, what you can see is a pretty similar trend. Despite starting at different temperatures, 20 meters beneath the Earth's surface. We're seeing this warming trend no matter where we go in Alaska. Temperatures of deep permafrost are warming. And when you look at the relationship between these permafrost temperatures and the kinds of warming that we're seeing at the surface of the Earth, they're pretty strongly correlated with one another. So permafrost is becoming warmer as a result of climate change. Now there's some wiggles in each of these records. They're not a nice straight line. There's some irregularities. And we understand why permafrost might respond a little bit differently to surface warming. It's a number of factors driven by the ecology, by the snow, different factors at the surface of the Earth, like snowpack, peat thickness. These are blankets that can act as insulating blankets on top of that permafrost. So some of these factors help explain some of those irregularities, but in general, we're seeing the same kind of movement in permafrost temperatures no matter what borehole we look at. So with warming at the surface of the Earth, we see warming of permafrost temperatures. We sort of know what's coming here. Whew, we call these spaghetti diagrams in science. This is actually a really interesting result of a model comparison study that we organized within the network that I founded called the Permafrost Carbon Network. Not all climate models simulate permafrost, so not all of them can actually look at permafrost, but of the ones that do, we started a study just to try to understand how they differ from one another in terms of making predictions about permafrost into the future. And this is the result of that model comparison study. Lots of variation. So each line, each color here represents an individual model. There's a couple of Canadian climate models represented here, and there's a lot of wiggles and there's a lot of spread. But again, we can explain some of that spread because we understand why the models differ from one another. Some include vegetation differently than others. Some are being driven by climate a little bit differently than others. So to some extent, we expect some variation. But look at the trends here across all of these models. They're all predicting widespread loss of permafrost area. And it's as a direct result of the kinds of permafrost warming that I showed you in those borehole records. So here's a great example of science. We have observations, long-term observations from borehole records. We have model simulations that are both converging on the same story. Permafrost is becoming vulnerable to climate change. It's warming, it's thawing. We're losing permafrost area. And we can see it. We see already the consequences of permafrost thaw. You take one visit to the north and you can see it. And this is what we find. Permafrost thaw affecting the infrastructure of the north, roads collapsing. As a result of frost heave, we see any kind of linear feature like railroads, trails, all kind of slumping and heaving as a result of those irregular thaw patterns. This is in the parking lot of the University of Alaska Fairbanks, where I hold adjunct status, and this is where I would normally park our field vehicle. Massive ice wedge failure caused a collapse of a big part of their parking lot, and this is slightly amusing because some of the world's best permafrost engineers work at this university. They built a parking lot on top of a massive ice wedge feature, and they lost half their parking lot overnight. So some of these things are really tricky to predict, even in the places where we need to predict them the most. The combination of permafrost thaw on land with global sea level rise of the ocean mean that storm surges are having more dramatic influence on coastline. Because of the Canadian archipelago, we have more coastline in this country than any other Arctic nation. And that coastline is becoming really vulnerable to massive erosional events. Again, this is the combination of thawing permafrost on land, triggering these instabilities so that when storm surges come, we literally see big chunks of earth falling into the ocean. There are settlements in places like northern Alaska, where their sacred lands are falling into the ocean. Settlements are being relocated in Alaska because of these kind of changes in coastline. We don't have the same kind of coastal communities in Canada, so this isn't on the front burners of northern governments as much as it is in Alaska. But nonetheless, we have quite a bit of terrestrial material that is just being deposited at mass into the ocean, and we know very little about the fate of this terrestrial material over time. Is it buried? Does it affect marine life? We really don't know. When we travel to northern communities and engage with elders and others in the community to understand what their concerns are, they may not say we're interested in permafrost thaw, but ultimately the conversation always comes back to some of their concerns about loss of frozen ground. So how permafrost thaw is even influencing the perception of land use is really important in terms of driving the way we do research. We know that instability and slumping of permafrost near fisheries is influencing the quality of spawning sites. You know, very important interactions along rivers that are used for access, just travel to the land. The bottom picture here shows a community member in the Northwest Territories, near a community that we work very frequently in, and he is standing next to his cross-generational, so very long-term trap line. This used to be a trap line that was forested, and they would hunt forest mammals for generations. In a period of about 5 or 6 years, this permafrost underlain forest turned into a very soupy, muskeg, what we call a collapsed scar bog. It is impassable in the summer. You can't walk across it. You can't drive across it with a skidoo. It's impassable. And so he is no longer able to access his land that's been in his family in use for generations. Not only does permafrost thaw influence land use, but traditional knowledge is influential in how we study permafrost. So there's a really nice feedback between sort of ways of living in the North and scientific studies. So for example, there have been several instances where community members have sent our research group photos. This used to be a lake. We used to fish here. The elders have stories about fishing here. Look at it now. It's drained. When you go and use remote sensing to look at that place on Earth, we see it. The lake has completely disappeared within 1 year's time. So traditional land use helps clue us into where the big changes are happening in land or water. In places like Russia and in Finland, ice cellars, permafrost freezers. We store our beer that way in the field, but these are used for preservation of food, much more important uses of permafrost. And we have a lot of temperature records from these kinds of ice cellars where they're not actually cold enough to safely preserve food anymore. So this is another area where traditional knowledge and data collected by community members can actually help fill in gaps in our understanding. And so this brings me to the second paradox. The first paradox was within myself. The second paradox that I want to introduce to you is that in a lot of circumstances, northern ways of living simply rely on cold temperatures in the winter. We are just at the start of our spring. We're very happy to be seeing the change in temperature. The sun just feels warmer, doesn't it? And I think a lot of us are ready to celebrate. But when you work in the North and you live in the North, the end of winter actually makes life really difficult sometimes. So in the winter, the whole ground is frozen. The whole ground is accessible, whether it be for trucking, medicine, and food to northern communities along ice roads, and maybe some of you are fans of ice road truckers. Truly, these are communities that are fly-in access only in the summer, but they're drivable in the winter, and families make use of this. There have been several times where I have literally felt that I have been in the middle of nowhere in the north. I've skidooed in to sample. In the winter, we do less damage that way. I feel like there's nobody around me for miles and miles and miles, and I love that feeling. And then a minivan drives up behind me, full of kids and full of, moms taking their kids down to the big city to do some shopping. You realize the world is more connected than you think. That kind of access only happens in the winter. Individuals traveling across their lands, across their trap lines, much easier in the winter. A lot of northern living revolves around winter sports. So they embrace the cold, and in fact, when you work long enough in the north, you hear this phrase: we have the right to be cold. And that is because northern ways of living are defined by cold conditions. Cold conditions in the air, cold conditions in the ground. And yet, through our day-to-day actions, we are taking away their right to be cold. And what happens in the north does not stay in the north. So what I want to shift to now is how these changes in northern communities and northern carbon pools can influence the whole global climate system. What I've done here is I've just grabbed snapshots of media story headlines that have happened in the past 10 years, and actually the Washington Post just featured a big article about permafrost and methane emissions that I was featured in yesterday, had a similar kind of scary headline. The tipping or ticking time bomb. We're scarily close to this tipping point. It's all bad. And in fact, we are doomed. Now, I work really closely with a really good group of journalists. We work really closely to make sure that the science is well represented. But even the best story, for example, this Washington Post story, I thought was very accurate, gets taken over by a headline editor, entirely different journalists. I have never worked with a headline editor, and they come up with these flashy articles meant to grab your attention. So what is this all about? There is a back between permafrost and the amount of carbon. This is basically dead mammoth and plant material from the Pleistocene era, from the early Holocene, that's been stored in permafrost soils. It's been frozen for millennia, maybe thousands of years, and now it's being exposed to warmer conditions. There's a potential feedback between that carbon pool sitting in permafrost, which is twice as much carbon as is contained in the atmosphere today, and how that carbon might influence the global climate. So I'm just going to walk you through this potential feedback. It is known to be one of the most likely feedbacks between the biosphere, between Earth and the global climate system in the coming few centuries. And it's known as the permafrost carbon feedback to climate. And it's a positive feedback, so let me walk you through this. So again, we have our little permafrost ecosystem at the center. We've got our thawing soils at the surface. So this is the seasonal thawed material. It's frozen in the winter and then it thaws out in the summer. But as you dig deeper and deeper down, you hit that perennially frozen ground that is called permafrost. What we're seeing as a result of climate change is that active layer, that seasonally thawed zone, is starting to push deeper and deeper into surface permafrost. And so that is exposing surface permafrost layers. Again, it's been frozen, locked up in an ice box for a very long time. And it's allowing microbes in the soil to start waking up. They're there. They're in the permafrost. We know it from microbial genomics. They are there, and they are ready, poised and ready. When things warm up, they start firing their respiration engines. Microbial respiration of soil organic matter produces two greenhouse gases: carbon dioxide under oxygen-rich or aerobic conditions, and when oxygen becomes depleted, anaerobic bacteria can produce both CO2, carbon dioxide, and methane, CH4. Methane's a really potent greenhouse gas. The diffusional gradient for these greenhouse gases is up, and so these soil gases diffuse right through the soil column, up through the vegetation layer, and into the atmosphere, where those greenhouse gases contribute to the greenhouse gas effect. More warming, more thawing of permafrost. It's positive, positive, positive effects all the way around the circle. This is what we call a positive feedback cycle. The media likes to call it the runaway train scenario, and I try not to encourage that, and yet sometimes the headline editors do take over. Now that's one kind of permafrost thaw, that slow, gradual deepening of that surface permafrost, that seasonal active pushing into the surface permafrost, and that's happening all over the north. Slow, gradual rates of warming of surface permafrost. There's a second kind of permafrost thaw. We often call it abrupt thaw. The more technical term is thermokarst. So karst just means slumping, thermo means temperature. So this is slumping of the land surface that happens when permafrost thaws, and this happens in areas when permafrost has a lot of ice in it. So when you get permafrost underlying wetlands or peaty systems or lakes, that permafrost actually has a lot of water in it. And what happens when that water starts to melt and thaw out is the whole land just collapses right down, right? Ice cube takes up more volume than water in its liquid state. So here's a massive ice wedge in Russia. This is just awesome. We don't rarely get an exposed face of soil to be in view like this. This is on a riverbank that's been kind of eroded away, and that's exposed this massive ice wedge feature. 100% ice, a little dirty, but 100% ice. Just think of what's going to happen to the soil on top of that ice wedge when that ice starts to melt out. The whole thing literally collapses. And that's exactly what we see in a lot of our field sites. Forests thawing, undergoing slumping due to thermokarst, turn into this. These are called thaw lakes. These can form as quickly as within a year to a couple of years. It's a complete ecosystem state change. Trees used to be present in this area of water. All the trees that used to be present start to fall over, and they're all underneath water. They get buried. So this has been a big uncertainty. This is a known unknown. There are known knowns, and there are unknown knowns, and there are unknown unknowns. So this is clearly a known unknown. No global scale or even regional scale model will currently touch this issue of thermokarst. It's too complicated. It happens vertically, and it happens horizontally, and it leads to these abrupt state changes in all aspects of the ecosystem. And the modelers that I work with just laugh nervously and sort of walk away when I raise this issue. So right now, they are modeling very simple representations of permafrost thaw. They're not measuring this kind of abrupt thaw. And so I have taken it on as a personal mission to convince the global modeling community that if they don't bring this into their simulation frameworks, they're missing the boat on the permafrost carbon feedback. So what my lab has done over the last 5 or 6 years is we've tackled a number of kind of simple questions, but they've been really difficult to answer. The first question is, where is thermokarst happening now? And where is it likely to happen in the future? So this is work that a postdoc of my lab, David Olefelt, he's now in a faculty position of his own at the University of Alberta. We set together to create a spatial mapping and modeling framework to understand all the way across the circumarctic where thermokarst is likely to occur. So we call these vulnerability maps. And what we have as a result of this study is a pretty good sense of what regions of the Arctic have ice-rich permafrost and are vulnerable to these kinds of abrupt state changes. So once we got a better sense of where this was happening, we could start to ask questions like, well, how much of the Arctic is vulnerable to thermokarst? It's about 15%. So these are narrow components of the land that have a lot of ice-rich permafrost vulnerable to this process. I'm not going to show you data on this, but what I'm currently working on is trying to link this up with a global carbon model. So we can actually measure carbon fluxes as ecosystems undergo that state change. So when they go from that nice stable permafrost to that thaw lake, like in the picture I showed you earlier. But then those systems, they undergo change, just like all ecosystems do. They undergo ecological succession. They maybe start to recover and accumulate carbon again through biomass. I'm an ecologist. I'm interested in that full life cycle of ecosystem carbon behavior. So we're linking what we know about Thermokarst today to these simple carbon models. And what I can tell you is that I think now the global modeling community is taking us seriously, because what we can show is that even though Thermokarst, or these abrupt thaw mechanisms, affect only 10 to 15% of the Arctic, they release as much carbon to the atmosphere as that really simple, gradual active layer deepening that happens everywhere in the Arctic. So these are truly large hotspot emissions. Hard to represent, of course, hard to represent in a simulation framework, but worth the investment. So now we're working with a number of different global scale models to bring this information in. It's very exciting. Okay. I want to introduce you to one of my colleagues, Katie Walter Anthony, but I'm going to zoom forward. Sorry, Katie, if I can. Oh, come on. All right, close enough.
Methane is a very potent greenhouse gas. A molecule of methane is 25 times stronger than carbon dioxide. Methane is formed in millions of lakes around the Arctic where permafrost is thawing. And each year, these lakes are emitting already tremendous amounts of methane. But when we look at how much carbon is in permafrost still frozen, and the potential for that permafrost to thaw in the future, we estimate that more than 10 times the amount of methane that's right now in the atmosphere will come out of these lakes.
All right. Lighting stuff on fire, something we're pretty good at. How about next? Next. Sorry, I'm a Mac user. Coral! Ah! Left side? Oh, thank you. Left side. I don't use PCs anymore. All right. So I wanted to show you that methane clip. You know, Katie and I often pair up. She measures methane fluxes from Arctic lakes. We measure methane fluxes from Arctic wetlands. We can light our methane on fire as well, but we can't stand on the surface of our lakes, on our ecosystems like she can. But it's a really critical issue because this gets at the heart of what this Washington Post article was about yesterday. We can make projections about the total amount of permafrost carbon that's likely to leave the soil and sediment and move into the atmosphere. We have those projections. We're narrowing down the window of uncertainty, or sort of the realm of possibility, but that's not enough. We need to know what total carbon is going to be emitted as CO2 versus methane. They have very different impacts on the atmosphere. Methane is 30 to 50 times more powerful in how it can trap radiation and contribute to the greenhouse gas effect relative to CO2. So how we partition those fluxes in our models and in our measurements between CO2 and methane, they really matter. And we have absolutely no agreement in the scientific community on this. The measurements and estimations in the literature vary by several orders of magnitude. So this is going to be the next challenge for our international research network. I think we've done a great job narrowing down sort of how much carbon might be lost, but now we need to work on partitioning that carbon. It's a big uncertainty. Again, a known unknown for us. And so this does bring me, this is all doom and gloom, right? All of those headlines sound kind of eerily fitting for the kind of story I just gave you. I will say that there is some good news in the permafrost carbon feedback to climate. About 15 years ago, there were some model projections suggesting that there would be enough carbon released from the north to cause disruptive climate change. So, you know, the movie The Day After Tomorrow, that kind of stuff. Those were what the early scientific estimations were. They were that scary. We've completely revised those estimates. So losses of carbon are going to be very large from the north. They're equivalent to about another industrial China on top of emissions, but they are going to be rather gradual and slow, building up, you know, over the next century or two. So it's going to be, we like to call this a knob or a dial on the current climate change system. We're going to turn up that dial. We are not actually going to cause a new, abruptly different climate system. That's actually a breakthrough. We did not know that about 10, 15 years ago. So we still have to deal with this issue, but it's not, you know, we're not all completely doomed. There's still hope. And in fact, if we curb our emissions and curb it to some of the more modest IPCC scenarios, we can actually prevent a lot of that carbon from coming out of the soils at all in the north. So we still have hope. So I want to talk about some of the better, good news aspects of climate change, because it isn't all doom and gloom. And when we work in the north, you know, we get questions equally from northerners about perennial frozen ground and how is that going to affect wildfire, how's that going to affect my family, but also some of these opportunities. They're very hopeful in the north. So there are a lot of good news scenarios. And one is that the north is being increasingly seen as a potential agricultural frontier. And every northern government has this pinned to their desk, and they are all working on agricultural productivity as a potential economic opportunity. So I do research in the Northwest Territories. They are one of the few northern governments that's released a formal food policy, and that policy recognizes agriculture as a very small economic, sort of viable route today, but it projects it to grow tenfold in the next few decades. They don't know how they're going to get there, but they know they need to reach out to researchers to do this in a smart way. So we are engaged in a lot of series of talks with the government of the Northwest Territories about what expanding crop ranges with warming means for their land and how they can embrace this. There's a dire food insecurity problem in the north right now. Highest rates of food insecurity in Canada are northern, largely indigenous households. And I didn't sort of phrase this as a paradox, but communities that become connected by the road system become much less stable and much less food secure. So food insecurity in the north is actually linked to road access. And it's because communities become detached from what we call country foods, from traditional harvesting of foods. And these are some of the communities that are really facing hunger and poverty issues. They're driving to the store, they have access to purchasing food, but a gallon of milk costs $25. So, you know, solving that food security and creating a new economic opportunity in the north is extremely attractive, as you can understand, to northern governments. But there's very little data on how we can manage this. Particularly because most of these soils are underlain by permafrost. You know, we talk about permafrost farmers, and I work with permafrost farmers. They're a hardy bunch of farmers. They're there, and they have great ways of managing permafrost soils, but how this can ever be expanded to a large scale is a little bit difficult to conceive of right now. And we only have to look to the last global agricultural frontier to take some important lessons home. When I was a student, if you told me you could build a viable economic industry farming tropical peat soils, I would have laughed. And yet, over the past 10 to 20 years, that's exactly what's happened in places like Malaysia. Most of tropical peatlands today have actually been converted for plantation farming. And there's a variety of different crops grown on tropical soils. Peat soils, when you drain them, when you warm them up, they have a lot of organic matter and they have a lot of nitrogen. They're very productive. And so certainly tropical peatlands have seen this kind of increase in economic viability. But it comes at a cost. You can't have production on tropical peat soils without getting rid of the water. So they drain these peat soils or muck soils, and then you can grow crops on them. There's nothing that burns better than drained peat soils. And so when you hear about tropical peat fires in Malaysia shutting down airports, causing havoc on, human health conditions in places like Malaysia, that is these drained peatlands catching fire and they smolder, so they burn for many, many months. It's a big air quality issue in the tropics. We also see it in global atmospheric carbon concentrations. In years where tropical peats catch fire, it releases so much carbon that we can detect an impact on the atmosphere. We have all those same conditions in the north. So this is a picture of wildfire creeping eerily close to the apex sites. This is a long-term experimental site that my group works in outside of Fairbanks. This is a really wet, peaty, muskeggy area. We have a ton of infrastructure, and this wildfire is getting really, really close. Peat in the north burns when it's dry enough. So if we have northern farming that diverts water away from those peat soils to make them more productive, we have all those same elements at play like the tropical system. We have large-ranging wildfires. We have a lot of organic matter in the soils. Under the right kinds of dry conditions, those will burn. And our fires also last for months. So fire has to be part of this story of developing northern agriculture in sustainable ways. And so we're talking actively with northern governments about pilot studies to think about how to embrace carbon-smart production. What carbon-smart agriculture will mean in the north is going to be extremely different than what it means down here in Ontario. We cannot import the same lessons that we've learned about organic matter management from Ontario soils, for example. We can't simply export those to the north. Some of these have to be bred in the north for the north kind of solution. But there's a lot of interest in doing this. So there will be a lot of work ongoing starting this summer, and some of this is in affiliation with the Arel Food Institute here at the University of Guelph. And so we often hear something that's called the paradox of northern climate change, or the Arctic paradox. And this is the good news, bad news play on climate change. To many, when they hear climate change in the Arctic, they think doom and gloom. Loss of infrastructure, massive loss of permafrost carbon to the atmosphere, disrupting Earth's climate. Those are the gloom scenarios. But others see opportunity. I'm going to play this back and forth. Here are changes over a couple years period of ice in the Northern Passage. Okay, so just a few years, look at that. The Northern Passage, it's patchy, but it's been ice-free and it's been navigable every year, since 2007. Okay, and we're obviously losing that ice every year more and more. With that comes massive economic opportunity and big opportunities for development. Again, sustainability is going to be at the heart of these kind of discussions. So I think we're learning more about those known unknowns. We've greatly downscaled or reduced the estimates of permafrost carbon losses to the atmosphere. We know now that it's not going to be nearly the kind of catastrophic loss of carbon that it was first projected to be. It's still going to be large, but it's nowhere near total global fossil fuel emissions. Again, it's sort of like adding another China. So that's a pretty big addition to global fossil fuel emissions, but we're not going to double anthropogenic emissions. Probably becoming more important to me as time goes on. Permafrost thaw and just changes on the land affects every aspect of northern ways of living. And it's just fascinating to work on a topic that is so cross-cutting. It cuts across society, infrastructure, ecology. It's really one of these themes that just kind of unifies all aspects of northern ways of living together. And that really kind of grabs me, keeps bringing me back to the north. And so obviously our work, it really engages Northerners. I think we're tightly coupled with a lot of stakeholder needs in the north. But because what happens in the north does not stay in the north, our work on northern carbon fluxes links us all together. The climate change from emissions that we're causing here in southern Canada is affecting northern carbon fluxes. Those carbon fluxes in the north are affecting climate change all around the world. So we really are in this together. This is a closed system, folks. So we're all integrated through things like carbon fluxes. And that's why I come back to Canada as a permafrost nation. It's a really play on words in a number of different ways. And so this is my last paradox, and I will use these sticky notes pretty soon. How can something so old and rugged and vistas like this, the north is full of rock and Pleistocene mammoth bones falling out of the soil, big sky, northern lights, it feels impenetrable. But these ecosystems are so incredibly sensitive to climate change. We're starting to get a better sense of how ecosystems may cope with some levels of climate change, but in some ways we know we've totally outpaced northern community change already. So this kind of balance between ruggedness and sensitivity is my final paradox. So here's where I kind of want to get your thoughts. I want you to finish this sentence for me. Bring your own perspectives to the table. I know just from chatting around the room, some of you guys work with me in the north, so I know you've been to the north. Some of you have worked in the north in other contexts. Even if you haven't, even if you want to go to the north, bring your perspectives and your worldview to finish this sentence for me. And then we're going to go around, my helpers, and we're going to try to group these. And I know we'll have some chance for question-answer period after that, but hopefully I can get your thoughts on that sentence right now. Thank you. Those are all great questions, and I'm happy to continue this conversation. This is my only similarity with Donald Trump. I do use Twitter to directly engage with people. I promise to be more sane and well-spoken. But I was going to say, if some of you, I'm linked with already, if you're on Twitter, please link up with me because I'm going to do conceptual mapping of your sticky notes and create some kind of word cloud with it. I'm really interested in sort of this paradox of the good and the bad, and so I'll be curious to think of your responses within the context of that paradox. And so if you link up with me, you can see what comes about, or you're welcome to email me as well on campus. I'll stick around for a few more minutes, but thank you guys very much for coming, and thanks for organizing.
As Dr. Turetsky said, she will be around for a few more minutes. You're also welcome to stay around for a few more minutes if you'd like to mingle amongst yourselves. Otherwise, thank you so much for coming out. We've had a fantastic time having you. We hope we see you again in the future.
And thanks, Coral, for all the technical assistance.